Yeah, screen is visible. Is it visible?
Yes, sir.
Yeah. So uh,
Yes, sir.
we have so far just concluding remarks on the first unit part. That is, we have in this unit we have seen the basic semiconductor materials, doped and undoped. It's the basic electrical properties. So the reason for we were doing was to is expected to take a step towards understanding the utility of make semiconductors when making semiconductor devices, and then of course ultimate objective of all these semiconductor devices is to make circuits, and which in turn will give us the electronic systems. So this so today's lecture we will have some concluding points about the extrinsic semiconductor. Two parts. One is some concluding remarks about the extrinsic semiconductors. Then the most important thing, which all this exercise was for finding out the current. What are the types of current and what are the factors on which the current in a semiconductor depends on. So we will try to get the expression for the currents, and which in turn will be used throughout all the other units actually. So that is a very important point we will be discussing. So these two aspects. So we'll spend some time in concluding the extrinsic semiconductors. Yeah. So this is one thing. Just actually, I wanted to show it as conductivity versus temperature. Very often, it is one of the most important property. Most of the textbooks will be giving you this. So, but I could not get that graph readily. So, I am just showing is the carrier concentration versus the temperature. It is more or less similar or as to the conductivity, because conductivity is basically, as far as the semiconductor is concerned, the conductivity is controlled by the carrier concentration, because the mobility is of course there is a decrease in the mobility, so there will be a slight reduction due to that, but the overall, because conduct carrier concentration varies exponentially with the temperature, so the dominating factor for the conductivity is the, as well with the temperature, is the change in the carrier concentration. So I am plotting, this is for an n type semiconductor. So you see that this if you can see towards the left side, it's a low like so of the order of 0 Kelvin or very low temperature. The impurities are not ionized fully. So this at least very low temperature, you have the impurity freeze out, which we talked of. So this region will have impurity freeze out, and then as we increase, the impurities will start ionizing, and so it will start contributing electrons. And then this region is popularly known as extrinsic region, because this is most of the impurities are ionized, so the conductivity or the carrier concentration is decided by the dopant actually. So this is typically known as, in the conductivity also, this region is known as the extrinsic region. And then of course the normal room temperature and above, you see this kind of behavior, intrinsic uh, region, where your intrinsic excitation, that means carriers are going from valence band to the conduction band. In this region you have the carriers coming from the uh, dopant levels. If n type, it is coming from the donors, and in the case of acceptors, the holes will be coming from the acceptor impurities. So that way, so this here, most of the impurities are ionized, so that there is no net variation in the carrier concentration. And then you have the normal intrinsic semiconductor, you have the carrier excitation with the temperature, room temperature and above. There will be a slight overlap here, because about room temperature, this intrinsic region, intrinsic behavior start dominating. So I would like to show this, because this was which probably you will be doing it in your characterization paper. So sorry. So this other otherwise you are supposed to do an experiment. So in the second semester, band gap measurement. So that you may basically change the conductivity with the temperature and plot the graph plot the graph between uh, uh, reciprocal of the temperature. It is 1 by T actually versus the conductivity. So in this, so naturally the intrinsic region will be this. So if you take the slope in this region, that is naturally it is a high temperature region, room temperature and above. Then you, from the slope you can find out the band gap. So this is what you do in your experiment of band gap measurement. And then you have this dopant. This is the extrinsic region. Sorry, this will be this is a extrinsic region, and then this will be your very low temperature. You have your freeze out and all those things will be there. So this is because I am plotting this graph or showing this graph uh, just to remind you that how band gap can be measured using conductivity measurement, which was a part of an experiment which you are supposed to be doing in the second semester. Probably you might be studying. I don't know. I'm not very sure about that part. Whether you will be studying it in your characterization paper. Because, recent changes in the syllabus might have happened, so I don't know right now whether it is there in the syllabus. But it was part of an experiment in this. So here and again, resistivity versus the dopant density. You can see that as you increase the dopant density, you can see that the resistivity decreases. So these are typical graphs. You can see. So now, before concluding our discussion on the extrinsic semiconductor, one question I would like to ask is, how will I suppose a wafer is given? If I want to know whether it's N type or P type, how will I know? Like, is there any way of, so suppose in a lab, I want to find out whether it is N type or P type. How will I know whether it is N type or P type? Yeah. Any answer? Hello? Anybody there?
Yes, sir.
How will you know a given wafer is N type or P type? How will I know? No idea?
No idea, sir.
Anybody else?
No, sir.
See, actually, one is if a full wafer is available, then one can know there are two primary and secondary flats, and the position of the primary. With if you go back to earlier discussion, we have discussed it in the first or second lecture or third lecture. I don't remember the lecture number. There you will be seeing that for the different orientations, there is a primary flat and a secondary flat. The placement of the primary flat, and I don't have the picture here today. So that is one way of, if any full wafer is there, then one can find out. But when in a typical lab like yours, there the very often a full wafer is not given to a student. You have a small piece of wafer only. I mean that means a part of it is a broken piece. So probably you might have done your experiment using broken pieces. So in that case, there is a simple. There are two techniques one can use. One is a very simple technique, which very often we used to do. I don't know nowadays we use this. Is very simple because most of the electronics lab there will be a soldering rod that is traditional. When you talk of microelectronics, normally that is missing, and with the development of breadboard and all those things, that is missing. But traditionally, in any electronic lab, you will be having a soldering rod. So you can take advantage of that soldering rod and do this simple experiment and find out the wafer. This is what. So this is technique. This is popularly known as a hot probe technique. So from cold, what is the voltage? So you can use a voltmeter or ammeter. and from the voltage or the direction of the current, one can find the type. I mean, it is you should not just touch it and go. That is all. Not for if you keep it for a long time, then steady state conditions, equilibrium will be established. You won't get it. So this was the experiment we used to do in our lab to find out the wafer, N type or P type. So you can see that if it is N type, the cold because you have majority carriers will be electrons. They will be reaching they will get take up the thermal energy and reach the cold point. So this will shown to be negative. And in the case of P type, the holes are the majority carriers, so they will move towards the cold side from pick up the thermal energy. So momentarily touching. So normally what we do is we connect this one wire terminal of this voltmeter will be connected to your soldering rod. The other, of course, will be the other terminal, so with the reference. So that is what we used to do. So this is a very simple experiment. One can do it in any electronic lab where the soldering rod is there. So this is the kind of simple experiment one can do. Yeah. So second one is a more elaborate one, which you might be remembering. What is the most elaborate one? Again, it is there in your syllabus. You will be doing it in detail in your paper which you are referring. That is the characterization. What is that? Any idea?
For probe.
Yeah, that is the whole effect study. So you can use the whole effect. So I'll just mention it here because you will be studying it in detail. Just we can see that you have a semiconductor slice. Then what is done is, so you can see that here you have a semiconductor, you have a electric field applied right in this direction. So there is a current flow in this direction. This is a slice. So I'm showing the three-dimensional view of this. Then what I'm doing is I'm applying a magnetic field perpendicular to this, or perpendicular to the electric field. So then what happens is we know that the charges can be influenced by the a magnetic field also. So what is the combined effect of or the combined force of electric and magnetic field? Do you have it? A separate name is there. What is
Lorentz
that?
force.
Yeah, it is
Lorentz
the
force.
Lorentz force. Lorentz force will be acting on these carriers when the magnetic field is applied. So it will be displaced. So you will see you see the lower part of this diagram. So you'll see that Lorentz force, the direction of the Lorentz force is in this. So if it is a P type, you have because they are the majority carriers are holes, so then you will be seeing a positive voltage here. And in the case of N type, if again the Lorentz force will be in the same direction, so you will be seeing a negative charge. So you will be so if you can get a voltage across this material, that is this is known as the whole voltage. So you can do the detailed derivation and all those things you will be studying, and I'm not going into those details. So you can find out the of course you can find out the type of the semiconductor, that is whether it is N type or P type. Then you can find out the carrier concentration, then you can find out the whole mobility, etc. So those things you will be dealing with in your paper, so you will be seeing it. But then I just wanted to mention that this whole probe is one of the most widely used characterization technique in semiconductors. So that is other way of finding out the type of dopant, whether it is N type or P type. And then here it is more elaborate, it's more qualitative, more quantitative in the sense you can find out the mobility, etc. So if you know the conductivity, you can find out the carrier concentration, etc. So that is now. Let us come to the second part of fun. That is one of the major thing we were always looking for this right from the day one. What are the types of current and what are the factors which decides the current? Because ultimately I apply a volt when you talk of a semiconductor device, what I do is I apply voltage and get the current. So what is the nature of the current with respect to voltage? That is the most important thing. So uh, we are going. We will see that there are you have two types of carriers involved, and what are the type of conduction process involved in the semiconductors, that and how they come about and how they affect the device performance. Uh, those are the things we will look into. Now we know that uh, in a normal any conductor, any electrical conductor, when you have a potential gradient, there will be a current flow. What do you mean by potential gradient? What is a
Change
potential?
in
Difference.
Uh,
potential.
what is a potential gradient? What is the other name for potential gradient?
Potential difference.
No, there is another word. What is the gradient of potential? What is gradient?
Elect-
Yeah. What is the
electric
gradient?
field.
Electric field. So electric field is nothing but the gradient of the potential. Is a spatial variation of the potential will give you. If there is a spatial variation of potential, that means there is there is an electric field existing. So if there is a potential gradient, there is a there is a tendency for carriers to flow. Then there is just like if you have a some potential energy is there, that can be changed into kinetic energy in the normal case. Then if there is a thermal gradient, what is the meaning of thermal gradient? What is the meaning of thermal gradient?
Change in temperature with respect to length.
Yeah, yeah. If there is a temperature gradient, then also carrier can take up the energy from heat. Thermal energy will be there. Then that is what we have seen in our first that hot probe technique. So it was taking up, and then the carriers were moving. Whenever there is a see, current means whenever the your charged particles, whether it is electrons, holes, or ions, whenever they make a displacement, you have the current actually. If net displacement is there, if there is net displacement is zero, then there won't be any current. But if there is a net displacement of the charged particles, whether it is electrons, holes, or ions, it will constitute a current. So thermal gradient can give. There are cases where thermal gradient will give, but we are not talking. We are talking of a constant temperature. Most of the time, semiconductor devices will be operated under constant temperature. So that thermal gradient we will not consider. But one of the most interesting thing about the semiconductor is the you can have a concentration gradient, because the carrier concentration can be different at different points. So if you can, so these two cases we generally consider. One case you have a potential gradient, that means an electric field is applied, and other case there is no need of any electric field. You have a concentration gradient is maintained. Then also there can be a current flow. So this is to us two types of currents in the semiconductors which we normally consider. So let us see. So the first one, when under the influence of the electric field, the current flow is normally known as the drift current. So you have see, when you are applying the electric field, they apply a certain force on the carriers, so they will pick up, the force will be equal to electric charge and field. So that will they will be accelerated. Force means there will be acceleration unless it is saturated. So that we are assuming that the saturation is not there. So you can see that the carriers will be moving. You can see that, you see carriers will be moving because of the scattering. It is not that they are going moving in straight line, which I have explained earlier. So you have found that the velocity of the carriers will be decided by a parameter, macroscopic parameter, mobility, and mobility into electric field was the velocity. So You can again, if you increase the temperature, the mobility decreases and all those things. So the carrier motion is not essentially straight line. There will be scattering and things like that. So, so this drift motion constitute this kind of thing. So they will normally we talk of an average velocity and the low electric field. They have the drift velocity will be much less than the thermal velocity, because otherwise also thermal energy is there. The carriers will be in random motion. So we talk of the thermal velocity, but drift velocity is normal. If under low electric field, the thermal velocity, the drift velocity is much small compared to the thermal velocity. So this right hand side, the current. So since you have two types of carriers, you have the uh, drift current due to electrons. So it is given by. So it depends on three things. One is the mobility of the carriers. It depends upon the concentration of the carriers and the electric field. Similarly, for the holes, it will be decided by the mobility of the holes and the concentration of the holes and the electric field. So these are the factors on which the drift current depends on. So the drift current is characterized by mobility. So you talk of a drift current, and it is applicable to almost all conductors. But so that is true for a semiconductor also. That when you have the change in uh, current with the electric field, and assuming that the mobility to be constant. We have seen all those things. You should remember that this doesn't, mobility can change with the electric field and all those things. I'm not going to that again, but we have studied that. But the general equation is this. So when we want to modify, you have to introduce, normally we assume that mobility is independent of the electric field, but high electric field mobility will be dependent on electric field. So if you look into any textbooks, you will be seeing that at high electric field, this is not treated to be a constant, so it will be changing with the electric field and all those things. So this is one component of the current, which is the drift component. So this the total. So since we have the this is velocity, and the velocity is given by this product of this, so that is how it is coming. So this is whole drift or drift motion or the drift current. So of course the current density. Yeah, it's not the current actually. J means the current density, current per unit area. So in general case, we consider both the contribution due to electrons and holes. So you have the hole drift current and the electron drift current. So since charges of electron and holes are different, they move in the opposite direction. But the conventional current will be same. Yeah, this electron will be moving in opposite to the electric field. Holes will be moving in this. So the total drift current will be in a typical semiconductor where both electrons and holes are there. Then you have this equation, the contribution due to electrons and contribution due to holes will come, and then you can write it as this is nothing but the Ohm's law. So you can see that this is basically the net conductivity multiplied by the electric field. So you have seen the carry electron concentration, mobility, the hole concentration, mobility of holes, and the electric field. So the conductivity is given by this, and of course, the reciprocal of the conductivity will be the resistivity. So this, as far as the drift current is concerned, this is one of the basic equation we will be using uh, throughout our further discussion. So you should keep this in mind. What is the drift current and how? What are the factors on which the drift current depends on? Now, one thing I would like to mention here, that even though we have shown the total current to be uh, electron drift current plus the whole drift current, very often we have either N-type or P-type semiconductors, so we can neglect the contribution other. For example, N-type semiconductors, we will be neglecting the contribution due to the holes, and similarly for P-type, we will be neglecting the contribution due to the electron. So those kind of approximations or simplification comes. So very seldom we consider all the components. Now this is one part of the story. Now so let us see. This is another interesting. This is very unique. So in fact, this makes semiconductors uh, very one of the most popular thing, especially for device applications. So even without the application of the electric field, you can create a current. So because as we have seen, for the current to be there, we need to have the carrier motion. So anything which causes the carrier displacement will cause the current flow. So we have seen that we can maintain a concentration gradient in this. And the physics says that whenever there is a concentration gradient, whether it is a neutral atom or whether it is of the charged particle or molecules, there will be diffusion. We have seen that that was the technique we use for diffusing for doping the material. We are using the diffusion technique because you keep a small quantity of the dopants and then you heat it, and then of course thermal energy also is there, but then basically it is the concentration gradient which is working on that. So they will be that those cases it was the neutral atoms or neutral molecules which were diffusing into the material. Now since when you have the doped semiconductor, and if it is the concentration is different at different points, that means the majority carrier concentration will be different at different points. Such a semiconductor is known as graded semiconductor. This I may not have mentioned earlier. So semiconductor where you have dopant variation from point to point, a spatial variation of dopant is there. Such semiconductors are known as graded semiconductors. It can be exponentially graded, it can be linearly graded, depending upon the variation of the dopant you can talk about. But graded means there is a uh, uh, concentration gradient exists from one point to other in the semiconductor. So it's just like the example I've shown here is you're putting a drop of ink on the top of this water, and then you will see that gradually those molecules or the of the ink will spread up. And if again it is not shown here, but what we'll see is it will be uniformly becoming the color of that ink actually. So it will be so you can do the simple experiment and see that how a small drop of ink will be making this whole water look like the color of the ink. So this is basically the diffusion process. So similarly, in a semiconductor also, you have a graded semiconductor. So let us say consider an N-type semiconductor. You have uh, so a non-uniformly doped or graded semiconductor. So you have see the higher concentration of electrons here, and you have the low concentration. So then naturally they will diffuse into this. So this is the basic process which we are talking of. But the thing is, since it is a charged particle in motion, so you have the current constituted by. In the case of doping, we did not see that, but in the case of graded semiconductor, you will be seeing that since the carriers are moving, they will be constituting a current, and that current is it's not due to the temperature, so it is due to the strictly due to the concentration gradient of the so the thermal energy will be more or less same actually. So again, your high school physics, you might have studied about, or in your graduation, you might have studied about Fick's law. That is, the flow is decided by the concentration gradient. So the current density will be decided by the concentration gradient. It's a one-dimensional case we are considering. So it is decided by dp by dx for the holes, and for the electrons, it will be decided by dn by dx. So the constant of proportionality is dn, the diffusion constant for the electrons, and for holes it is dp. This is the diffusion constant. So the total diffusion constant current, if both type of are there, then you can, just like in the case of drift current, you can write down this. Very seldom this kind of situation exists, because either it will be N type or a P type. So we may not have both, grading of both will not be there. But in general, we can write this. So when we talk of the total current in a semiconductor, we have four components. The two components of due to the hole, that is the hole drift current and the electron drift current, and the hole diffusion current and diffusion current due to electron. So you have four components, and but we'll always see that most of the time, one or two will be only dominating. So we need not worry. But in general, we can have four components of current. This is these two equation. This equation is the basic equation for current in a semiconductor. Total current is, of course, the current due to electrons and current due to the holes. I mean, I repeatedly mentioned that it's a current density we are talking of. It is not the current. So similar. And then electron have two parts. This is the electronic contribution, and this is the hole contribution. So you have this. So this is known as drift diffusion equation. So this is one of the most fundamental equation. Apart from the equations we have discussed earlier, that is the law of mass action. This is one of the most fundamental equation of the semiconductor, and it will be very often used for studying the electrical characteristics of your semiconductor. Now, so this just so very often nowadays we very often consider the three-dimensional view also, because very often the three-dimensional picture, so it will be coming in the gradient. So you have this. The one-dimensional, very often in the your case, you will be dealing with only the one-dimensional, but at the advanced level, you have this three-dimensional picture also. Of course, the electric field will be in one direction, but the concentration gradient could be in the three directions. So you can have a gradient actually instead of this dn by dx, you have this gradient coming for both electrons and the holes. So another interesting thing is the connection between the mobility and the diffusion constant. Actually, is there any connection between the mobility and the? If I know one, can I find out the other? So that is what. So that is popularly known as the Einstein relationship. So before that, let us look into relation between the energy diagram, potential, and the electric field. The energy, potential, and the electric field. So what is the relationship between the electric field and the potential? Yes.
So E equal to V by R, del U by del X.
Yeah, dV by dt. Yeah. And what is the relationship between the potential and energy? Is there any relationship between potential and energy? Yes. Any relationship between potential and energy? Any idea?
So half mv square, I think.
Yes. No. Potential is what is Q into V, the electronic charge and the voltage. Is the energy?
Yes, sir.
So electric field and the energy is related by this, because we can write energy, sorry, the electric field as you just look at this, it is visible, no? So it is dv by dx is the electric field, and this can be ec by q is v, because e is equal to qe. So ec by q is V. Okay.
Yes, sir. Got it.
So this is so you can see that. So this is very interesting result. So in the energy bank diagram, if you want to show the existence of electric field, we'll be showing a variation of the energy with this. So it will be, there will be a slope. So this is very important when you are drawing the band diagram. So normally we show the band diagram without any electric field. So it will be a straight line. But if there is a slope, so that is what is shown here in EC and EV, and that change will be proportional to the voltage you are applying. For example, you can see that you have applied a zero point 0.7. Oh, this is the energy actually. Zero point 0.7 EV means electron volt means the energy. So this is shown in as the, but we will be applying as a voltage. If you want to find out the voltage corresponding to that, you have to divide it by the electronic charge. So then you see that there is a slope in the energy band structure. It's not straight line. It will be slow, like this kind of change will be there with the X actually. Then we see that there is an electric field existing. So this is that comes through this equation actually. So this is very important when you are plotting the energy band diagram. We will be seeing when, say, for example, we are talking about various devices under non-equilibrium condition. That means we are applying electric field. How the band diagram will change. That is a very interesting thing. So, our when if there is an electric field existing within the semiconductor, then it has the energy band diagram. There will be a change in the energy band diagram. That will be corresponding to this actually. So this is one thing we should remember. So, so now let us get into Einstein relationship. So Einstein, the electron, let us take the N-type semiconductor. So we have seen that the electron concentration is decided by these factors. This is the density of states in the conduction band, and then this is the Fermi function or the probability function. So this again, I can do the differentiation. Dn by dx will be this. So this is dc by dx. So this I can see that. So from this, so this will be n kt by d by d. So this is, I can write it as, you just work it out and see. This will come as n by kt into qe. This is the from our earlier using making use of the earlier relationship. So you get this. So dn by dx at equilibrium. So now let us look into this equation. At equilibrium, so this point I did not tell you when we are talking about the diffusion. How in a graded semiconductor, how equilibrium is achieved? Any idea how equilibrium will be achieved? In the case of ink, we have seen how the equilibrium is achieved. What is the difference between the case of ink and the electron or in a hole flow? Is there any difference in the equilibrium conditions? Anybody? You got the question?
Yes, sir. Got it.
Yeah, yeah. So what is the difference in the equilibrium condition in these two cases? Any idea?
No idea, sir.
See, we have to understand. See, actually, initially, you had the charge neutrality existing throughout the semiconductor. Whereas in the case of a drop of ink falling on the into a beaker of water, we have the ink spreads out. There is no there is no question of any charge neutrality or anything. It is not disturbing anything. So what will happen is the ink molecules will be uniformly spread out. Whereas in the case of electron diffusing, what will happen is as soon as the electrons move away, that charge neutrality is violated. You have the electron moving, so there will be a donor ion which will be exposed. Similarly, for holes, an acceptor ion will be exposed. So there will be a gradual build-up of electric field. And at equilibrium, this is the situation. The net current will be zero. How? You have so equilibrium is shown to be, you are having, because of the electric field which was created by the diffusion of the carriers, there was a built-in electric field. And of course, there is a diffusion current. So you have a drift current and a diffusion current, and the net current is zero. So this is how equilibrium is achieved. You have a drift current and diffusion current which are cancelling each other. Of course, they will be in the opposite direction, so they will be cancelling. So that is giving the equilibrium. So you can see that, okay, then I can take advantage of this. I can replace E with this, so I can write down this equation and I can get this relationship between the dn and mu n. Dn by mu n will be, you will see that it is equal to kt by q. So this is known as the Einstein relation. You got the point. The equilibrium, under equilibrium condition, you have a equal and opposite diffusion and drift currents, which, and you have to understand how the drift current is coming. There is no external electric field applied. But what happens is, when the electrons or the holes are diffusing, they will cause a breakdown in cause a change in the electrical neutrality. So a built-in electric field will be created, which in turn will cause a drift current in the opposite direction. So at equilibrium, these two will get cancelled, and you get there will be not be any net current. So under the, initially when they make a device, you have that, or if there is a concentration gradient exists, then you have a the carriers try to diffuse, and then equilibrium will be immediately established by cancelling by built-in field and things like that. So you can see that the built-in field will be decided by the concentration gradient, etc. You can write from this equation, you can find out the built-in electric field. This is actually showing the built-in electric field. This E is showing the built-in electric field. So dn by mu n is kt by q. So similarly, one can use the same argument for the holes also. So dp by mu p is equal to kt by q. Kt by q is dimensionally. What is kt by q dimensionally? What is the dimensions of kt by q? Yes. What is kt? Yes.
K is Boltzmann constant, T is temperature.
What is kt? K is Boltzmann constant, T is temperature. That we know. But then what is kt? Yes. I've been repeatedly telling. Actually, I think most of you are not following the discussions here, because these things were repeatedly said. What is KT? So that is very unfortunate.
Energy.
Yes.
It is saying energy.
Yeah, it is the thermal energy. So energy by charge. Let us say this is energy. Energy by charge.
Voltage V.
Is voltage. Actually, this is popularly known as thermal voltage, because if it is expressed in electron volts and divided by Q, will give me it will have the dimensions of voltage. So this is popularly known as the thermal voltage. And in fact, it is of, in room temperature, it will be have a value of 24 to 26 uh, millivolt actually. So when we talk of a small signal, we generally define it in terms of this thermal voltage, because it's a very important parameter. That is why we spend some time on this understanding of KT by Q, because you will be very often applying voltage like some multiples of KT by Q, thermal voltage comparable to or much more than thermal voltage and things like that. We will be very often talking of that. So KT by Q will be a term which will be very often coming. KT comes from your kinetic theory of gases, because and that was that is incorporated into electrons also, thermal energy and things like that. But kT by Q is nothing but K, of course, will be expressed in electron volts unit. So kT is expressed in electron volts. Then you have kT by Q is the thermal voltage. So for a given temperature, kT by is constant. So you can see that dN by mu n or dP by mu p is constant. That is the thermal voltage. So this is popularly known as the Einstein relationship. Yeah. So I think I'll stop it here today. So if you have any questions, you can discuss that. Otherwise, I have the 3 questions for the day. Yeah. Any questions?
No, sir.
Yeah. Anybody else? Any questions?
No, sir.
So these 3 questions I am giving you. So this is first one is an engineering problem. So you have to see the practical application where minimum three of we can go beyond five also. Find out practical 3 to 5 applications of Hall effect. So you'll have to find because Hall effect is one uh, thing which has been widely used, including, for example, font. Very often, most of you are using a flat font. When you put the cover, it automatically the display goes off. So you will see that there Hall effect is used. There are, so you can see various those kind of everyday applications of Hall effect. So you have to list at least 3 to 5 different applications of Hall effect from everyday life. Then we need to see we have discussed 2 kinds of current flow. One is the drift flow and the other one is the diffusion. There are class of devices which are based on drift current, and there are class of semiconductor devices can be characterized in fact into 2 categories. One is the devices based on drift current and devices based on diffusion current. So you have to list some of these devices which are based on drift and diffusion current. So these are the, so you can try these questions and get some insight into these things. So with this, I think I'll stop it here today. Okay.
Yes, sir. Thank you, sir.
Thank you, sir.
Okay.